Hi everyone. In this video, I'm going to take you through a detailed analysis and review of the BetaFPV Pavo30 Cinewhoop. Firstly, I'm going to take you through all the components of this design on the bench so you can see exactly what we're working with. Then I'm going to show you some flight footage from the quad exactly as it came out of the box from BetaFPV. Then we're going to look at a black box analysis from the quad to identify some aspects of the design that are limiting the flight performance. And I'm going to show you some really minor modifications you can make to the BetaFPV Pavo30 to remove those limitations and vastly improve its flight performance. Finally, if that wasn't enough, I'm going to take you through my filter and PID tune for this quad so that you can get it flying just as good as it possibly can. And we're going to end with some flight footage showing how much of a difference all of that has made. There's no time to waste, so let's get into it. So let's take a look at the BetaFPV Pavo30 on the bench. Now the frame is constructed of three main parts. There's a top part, which is injection molded ABS plastic. There's a bottom part that's another large piece of injection molded ABS plastic that forms the prop guards and the mount for the Caddx Vista that you can see there. And the third structural element is a piece of 2.5mm thick carbon fiber. It's a single piece that's been CNC'd out along these struts that you can see here to form the support for the four motors. And these three elements are held together by a number of plastic self-tapping screws and by the motor screws as well. So they're pretty secure. They're not going to come apart even in quite a big crash. The camera that BetaFPV have chosen to use on this frame is the Caddx Nebula Nano camera. Now, this is not my favorite camera for the Caddx Vista. I would prefer something like the Nebula Pro, but that's not really available right now. So I think BetaFPV have chosen to go with a camera that they could actually get hold of. As for the electronics in this quad, it's pretty hard to get to it. But I've taken this quad apart and I can tell you that it's using the BetaFPV F722 35 amp all-in-one flight controller. And it's using obviously the Caddx Vista for both the control link, so it's using the DJI controller, and also for the VTX. There is a capacitor fitted to the power leads for the flight controller, which is a nice touch. And you can see that the connector that they've chosen to use for the battery is an XT30, which is, I think, a good choice for a 3-inch quad. They're using a left-hand circularly polarized antenna here mounted inside the ABS plastic shroud. So that's nice and secure. It's not going to vibrate and it's not going to go anywhere. And because it's inside plastic, it should have pretty good range as well. Up here at the front, you can see the fairly unique feature of the Pavo30, which we're going to be talking a lot about in this video, which is this vibration dampening camera mount. So it uses 3 silicone gummies and some plastic screws to vibration isolate the camera. And you can see it's very flexible and moves very easily. And we're going to talk more in the video about how that can actually create some problems when you're trying to tune this quad. One of the key limitations of the F722 flight controller that BetaFPV have chosen to use in this quad is that it doesn't have any black box logging. So I don't know how they expect you to fine-tune the performance of the quad or identify any issues, but there's no black box. So for the purposes of this video, I have connected a serial black box logger, the Open Lager, spelt like the beer, to this flight controller. And this is what I'm using to do all of my logging. Now, this Open Lager chip is capable of logging at least 2 kilohertz. And the baud rate that I have set here is 2 megabaud. So there's plenty of data rate to capture black box logging at a high enough frequency that we can do things like look at the spectrograms to tune the filters and the PIDs and that sort of thing. The motors that BetaFPV are using on this quad are the BetaFPV 1506 3000 kV motors. And that's a really large motor for a 3-inch prop. But you can see why they've chosen such a large motor. It's because they have these 5-blade, relatively steep pitch pusher props. And so they need a lot of torque to drive these props and create the thrust that they need to fly this thing around without the motors overheating and getting too hot. The dry weight of the quad is 172 grams, and I have chosen to fly it with a 850 milliamp hour 4S battery. And if you include that 4S battery, it comes to 270 grams. So I think it's conceivable that if you picked a lighter battery, maybe a 750 or a 650 milliamp hour, you could probably get this quad under 250 grams. But that, of course, doesn't include the weight of a camera. I've made up this dummy mass here to represent the mass of an Insta360 Go or a naked GoPro camera. And if we include the mass of all of this, we can see that the quad comes to just over 300 grams. So we've got about a minute of flight footage here for me to show you. And my experience with flying this quad out of the box was that it was very unstable in the air. There was a lot of wobbles and bobbles and really poor prop wash handling, which you'll see here. And all of these things together really took away my confidence with the quad. I didn't feel like I could trust the quad to go where I wanted it to go and do what I wanted it to do because of all these wobbles and bobbles and shakes. And you can see I hit the ground there because of that. So here I'm just really trying to test the limits of the quad and see how it behaves. And you can see that it's shimmering and shaking in the air. Now, before you get too disheartened looking at this, these issues we are completely able to fix and solve with just a few minor modifications. So let's take a look now at a black box log analysis of that flight to see if we can identify why we're seeing that poor flight performance, why we're seeing that poor prop wash handling and those wobbles and bobbles. What you're looking at here is a spectrogram of the data from the gyro on the roll axis. And this is before any filtering has been applied in the flight controller. And what you can see is that we have a few key features. This large peak here, close to 0 Hertz, is the real flight movement of the quad, the actual movement of the quad in the air. Then we see we have this broad hump of noise here. That is motor noise, so that's the vibrations being caused by the motors. And you can also see that we have these little spikes, and these are resonant frequencies of the quad. So these are frequencies where some part of the quad likes to vibrate, its natural frequency. And you can see that we're comparing these resonant frequencies against this list here. Now this is a list of the first 27 resonant modes of the Pavo30 frame. And I've created this list using a finite element simulation model of the frame. And you can see in some of my previous videos that I've spent quite a lot of time validating my simulations against real-world flight data so that you can be confident that what we find and predict from the simulation actually represents what we see in reality. And that's certainly the case here. We can see that the second resonant mode of the frame is clearly being excited by prop wash and is creating that really sharp resonant peak. Then there's an area where there's very little vibration, very little gyro noise, and we can see that we're not really exciting much in the way of resonant modes there. Then we get up to 150 Hertz and 170 Hertz, and these are the first few frame resonances that are to do with the movement of the motors on the arms. And then there are lots more of these frame resonances all across the frequency band, all the way up to about 400 Hertz. And of course, because they're resonant frequencies, there are an infinite number of resonant modes going up in frequency. So I'm just showing you the first 27 here because they're the ones that are most relevant. They're the ones that are going to be excited by the movement of the quad in the air and by the motors. If we look over here to the waterfall plot, this shows you the frequency of vibration that's being detected by the gyro and how that relates to throttle position. And what we can see here is we have these vertical lines, and these kind of vertical bright stripes indicate frame resonances. And you can also see there are these vertical stripes, but a broader band of high energy vibration here, which is the motor frequencies. So this is as we would expect. The main issue with this gyroscaled log is this peak at very low frequencies. Now, a flight controller has software filtering on the gyro to remove some of these high frequency vibrations up here. But there's really nothing to remove low frequency vibrations. And that's by design, because low frequency vibrations are often real flight effects, real aerodynamic effects that the flight controller needs to respond to. So whenever we have a resonant peak of vibration like this, down in those frequencies where real aerodynamic effects are happening, we're going to have problems. Now let's look at the pitch axis. And again, we see similar characteristics. This large peak close to zero is real movement of the quad, flight movement in the air. We have this really worrying peak at just about 30 Hertz. You can see that corresponds to the first resonant mode that was determined by the finite element simulation. And this mode is so close to the real flight frequencies of the quad that it's pretty much impossible to filter this out, and it's going to cause us a lot of problems. Higher frequencies in the motor band are easier to filter out, and actually there's not so much vibrational energy up here compared to the roll axis. If we look at the yaw axis, we can actually start seeing now some of these resonant modes, 3 to 6, starting to be excited and be visible on the yaw axis. And that's because of just how the camera in this case is moving. There's also a large spike at 200, and that's to do with this 9th resonant mode, which has the motors twisting on the end of the arms. We're not really going to focus on these for this video because I think the camera mount's more interesting, but you can see how the finite element simulation is predicting that these resonant peaks are going to occur. And that helps us validate the model and make sure that what the simulation is saying reflects reality. So now that we've identified that there are these two particularly problematic resonant modes, one at about 33 Hertz and one at about 50 Hertz, we can go to the finite element model and use something called harmonic analysis to visualize exactly how the parts of the quad are moving at those particular frequencies. And the way this works is by combining the effects of all the resonant modes together and then exciting the whole system at the target frequency and visualizing how the system is going to respond to that vibration. So if we excite the system at 33 Hertz, which was the frequency of that first resonant peak, we can see that it corresponds to the camera rocking back and forward on that flexible camera mount. And so you can see that it's the flexibility of the camera mount here that is causing the problem, because that's what's allowing the camera to rock back and forward, and that's what's creating that vibration at 33 Hertz. And this is the real power of harmonic analysis, is it lets you visualize exactly what's causing a peak of vibration in your black box log. Now let's look at what's happening at 50 Hertz. And you can see that again, it's the camera mount, but it's vibrating in a different way. This time it's rocking to the left and to the right rather than forward and backwards. And so again, it's the camera mount that is the cause of that vibration at about 50 Hertz. So this shows you some of the hidden dangers of vibration isolation. Now, vibration isolation for your HD camera initially sounds like a great idea, right? Well, we can separate the vibration of all the motors and everything on the quad from the camera, and I'll get beautifully smooth HD footage. That's true, but only if the vibration isolation is correctly designed. Otherwise, it's likely to make things much, much worse and not better. And that's what we see in this case with the Pavo30. The vibration isolation solution that they've chosen is actually making things worse, not better. If the damping ratio of the vibration isolation system is less than 1, which it is for the vast majority of mounting solutions, the system is actually going to amplify certain frequencies, and we can see that here. Now, I estimate the damping ratio of those silicon gummies at between 0.05 and 0.1. And what this means is that you get some really significant amplification of vibration at certain frequencies. And those frequencies depend on the natural frequency of the camera mount, which we can see in this case is about 33 Hertz for forward and backward, and about 50 Hertz for left and right. So how can we improve this? How can we design vibration isolation that is effective? Well, we have to consider that there are two sources of vibration on quadcopters, which we are typically most concerned about. There are prop wash vibrations, which typically occur up to a maximum of about 80 Hertz. And then there are motor vibrations, which occur at a frequency 1/60th of the motor RPMs. Now, a well-designed vibration isolation system will have prop wash frequencies occurring well below the region of amplification. So down here where the system is not amplifying vibrations at all. But we'll have motor frequencies well above the region of amplification to correctly attenuate the vibrations that are coming from the motors and props. And also, the system is going to have a damping ratio as close as possible to 1 to minimize any vibration amplification in this region. And the problem that we have with the Pavo30 solution is that out of the box, its region of amplification sits right on top of prop wash frequencies. And so it's amplifying the prop wash frequencies and it's making the prop wash a whole lot worse. So now that we understand this, we can go about making some modifications to improve the performance. Here are my recommendations, and I'm going to take you through each one of them step by step. Firstly, we're going to fix the camera mounting. We're going to modify the camera mount to greatly increase its natural frequency of vibration to move that region of amplification away from prop wash frequencies. Then we're going to enable bidirectional D-shot and RPM filtering by updating the ESC on that AIO flight controller to BLHeli-M. And the reason we're going to do that is because RPM filtering is a fantastic feature for reducing that large hump of noise that we saw that was created by motor vibration. Then once we've done that, we should have a really good platform to tune our filters, tune our PIDs, and finally, I'm going to show you some flight footage of how all these changes affect how the quad flies. Let me talk you through how I propose to improve this camera mount. Now, I've reversed all of the screws that were in the camera mount. So I think they used to have the heads on the top, and what I've done is I've now reversed it so the heads are on the bottom. And to do that, I've had to drill a 5mm diameter hole through the plastic just here with a drill bit, and that gives me access to put the screw in the other way around, and I can get a driver down to turn that screw. And all we're going to do to improve this mount is we're going to cinch all of these screws down tight as hard as we can to really take out any flexibility or movement in that camera mount. So I'm going to do that now. Now, once you've cinched these screws down really tight, you'll have this really large amount of protrusion of the screw. And so what I would suggest you do at this stage, once you're happy with how the mount is, and I'm very happy with that because of how stiff it is, it's not going to move around anymore. These are plastic screws, so just go ahead and get your wire cutters and just cut the screws off to shorten them. So to update the firmware on the ESC of your Pavo30 to enable bidirectional D-shot and RPM filtering, to start with, you're going to want to go to this web address, and I'll put a link to that down in the video description. This is the releases page for the Jazz Maverick edition of BLHeli Configurator. You can see that there are different zip folders for different operating systems. I'm on Windows, so I'm going to choose the Win32 version. If you're on Linux, you could pick one of the Linux versions, and there's a macOS version as well. So pick whichever one is right for you. Once you've downloaded that, go to where you downloaded the file and you'll see this zip folder. Go ahead and extract that and go into the zip folder and you'll find BL Heli Configurator EXE. So go ahead and run that. You'll see this screen. At this point, plug in your flight controller over USB and also plug in a battery to your ESC. Come up into the top right and select the correct port for your flight controller. For mine, it's COM3, and click Connect. Then read Setup. Now you should see this screen where you have 4 ESCs with different versions. Yours will probably say 16.7. To update your ESCs, go down here and click Flash All. Select 16.9, BL Heli M Official, and leave the target alone. So it should say GH30, but just leave it alone. And then click Flash. Now the configurator will flash and update all your ESCs. Once that's complete, you're going to want to set up the settings for your ESCs to get the most out of your motors. I'm going to show you the settings I use now. These are my recommended settings for the ESC on the Pavo30 running BL Heli M 16.9. And the only things I've changed from default is the PWM frequency, which I've moved up to 48 kHz, which will provide a little bit of additional efficiency and flight time. And I've also changed the motor timing to medium-high to give a little bit more protection against desyncs and a little bit more low-end torque and responsiveness. Don't change the motor direction in BL Heli M. This should persist when you update your ESC firmware and should be set correctly from the factory. So now we have our ESC set correctly, it's time to go into Betaflight Configurator and set up our filters and our PIDs correctly. And we're going to do that by going in and connecting to our flight controller. And then we're first going to go into configuration. And under ESC and motor features, we're going to make sure we tick bidirectional D-shot. You might also want to set the motor idle throttle value to 5.5% and check that the motor poles is set to 14, which it should be. Once that's done, you've enabled bidirectional D-shot, so go ahead and hit save and reboot. So now let's go in and set up our filter and PID tune. This is under the PID tuning section and filter settings. We want a single gyro low pass at 500 Hz PT1 type with 3 filter harmonics for the RPM filter and a dynamic notch setting of 0, 250, 120 and 450 for this particular quad. And then for D-term low pass, we want a single static biquad at 100 Hz. Once you've got all that set, hit save and then go into the PID profile settings tab. Increase the master multiplier to about 1.4, I found was good for me with the naked GoPro on. But you might want to increase in steps of 0.1 or 0.2 to find the right level for you. And then I have stick response gain set to 1.5 so that I get a nice snappy entry into sharp moves. But if you're looking for a smoother, more cinematic style of flying, you should probably leave that at 1.0 or even reduce it. I've also set up dynamic idle at 2,400 RPM. Once you've got all those settings set, hit save, and that should give you a really good starting point for your filter and PID tune on this quad. Here's another minute of flight footage to show the difference that all of these changes have made. And I really think that the best way to show off a tune for a quad is to fly it hard and aggressively. So that's what I'm doing here. Now I know that this is a Cinewhoop, so you probably wouldn't fly it like this in reality, but I think this shows what the quad is capable of with just a few modifications and a proper filter and PID tune. You can see that we really don't have any of the wobbles and bobbles that we had in the first flight. And you can probably tell from my flying that I'm a lot more confident with the quad. I'm more confident that it's not going to have horrible prop wash oscillation when I fall into my own prop wash. and I can even do some quite dynamic freestyle moves with it. All in all, for just a few minutes of effort, tightening up a few screws and doing a little bit of filter and PID tuning, the improvement in flight performance that we can get is really good to see. And I would be more than happy to fly this quad, not just for cinematic stuff, but also just a little bit of fun freestyle as well. I hope you enjoyed this analysis and review of the BetaFPV Pavo30. I think we got it flying pretty good in the end. If you'd like to pick up one of these drones, I'll put a link down in the video description to somewhere where you can buy one. It's an affiliate link, so if you use it, you'll also help support the channel. If you like the work that I do, I also have a Patreon. For less than the price of a coffee, you can join my Discord server and get sneak peeks of all the projects that I'm working on. I'm currently working on a 7-inch long-range frame, a 5-inch racing frame, and a new type of carbon fiber. So if you don't want to miss out on information about those, then I'll put a link to my Patreon down in the video description and in the end cards of this video. That's all I have for you for now. So until next time, I wish you all very, very happy flying.